Good morning to everybody. It's time for a new data science seminar, and today we will welcome Christina Heinze-Deml. She's a senior postdoc and lecturer at the Seminar of Statistics at the ETH Zurich, and she did her PhD at Nikolai Mainshausen and Jonas Peters at the Department of Mathematics, also in Zurich, and she also spent some time at Facebook AI Research and DeepMind. And today she will talk about active invariant causal predictions, experiment selection through usability, and we are happy to have her here. Now it's your turn, Christina. Have fun.
Okay. Well, thank you very much for the introduction. So before I start, I want to already give you the very broad picture of what this talk is going to be about. So I was already saying it a few minutes ago, so this is about causal structure learning. So we're in a setting where we have data from a number of variables, and we want to estimate the underlying causal structure or graph of the system based on this data. And now the setting we look at here is called an active causal learning setting. And that means that while we're trying to estimate the causal structure, we have the ability to actively perform experiments, also called interventions in causal language, that then allow us to gather additional data points that then hopefully help us for the estimation problem. So this is what this active denotes in the title. And invariant causal prediction, that is the causal discovery method that this work is based on. Now, this is a joint work with Juan Gamella, and I should really say he's the mastermind behind this work, and a lot of the credit should go to him. So in terms of the outline of this talk, so I'll spend quite a lot of time on background material because I assume that not everyone in the audience has had exposure to these ideas. So first, I'll provide some background on causal modeling and sort of the general frameworks that are used there. Then I'll introduce this problem setting of active causal learning in a bit more detail. And then I'll go into sort of the building blocks that we use for our method of active invariant causal predictions. And these building blocks are this invariant causal prediction method and so-called intervention stable sets. So for causal modeling, there are a number of frameworks. So one framework uses so-called structural equations and causal graphical models. So in our setting, there is one response variable y of interest. So you can see that here in blue in the graph on the right. And then there are a number of predictor variables, x1 up to xp. And then the causal graph is a directed graph. It's typically assumed to be acyclic, and it describes the causal relations between the variables. So for instance, here, x2 and x3 have a directed arrow into y, which means that x2 and x3 have a direct causal effect on y. And then we also say that x2 and x3 are so-called causal parents of y. And here throughout, we denote this set of causal parents of y by S star. And in fact, later on, we will be interested in just finding the causal parents of some variable of interest rather than estimating the whole causal graph. So then along with this graph, you have a set of so-called structural equations where you write each variable as a function of its causal parents and a noise term. And these structural equations really describe the data generating process. So now this framework helps us to understand to some extent why causal inference is quite difficult. Namely, it turns out that many structural equation models generate the same observational distribution. So here on the slide, we see three different underlying causal graphs, and then we look at the distribution between x and y in these plots. And as you can see, we get exactly the same observational distribution, And when we fit a linear regression to predict y from x here, we get exactly the same result. So when you compare the fitted regression lines in these 3 plots, for instance, you see that they are exactly identical. So from the data, we cannot say which causal model it was generated by. And this is what is meant by the following statement, namely that complete knowledge of an observational distribution usually does not determine the underlying causal model. Now you may notice this term observational distribution, and that is, so we stress this fact that it's observational because in causal inference we differentiate between the observational distribution and so-called interventional distributions. So what are interventions in the first place? So interventions model what happens when the system changes in certain ways, when we intervene on some of the variables. So that's also causal terminology, this notion of intervention. But more in broader terms, you can also think of this as performing an experiment and thereby changing the system to some extent. And here in this framework of the structural equations, an intervention on a certain variable is modeled by replacing the corresponding structural equation. So there are different types of so-called interventions. So on the left, I'm showing a so-called shift intervention, where one would add an additional noise term to this generating equation of the corresponding variable. On the right, I'm showing a do intervention, where we then replace the corresponding structural equation entirely, and here, for instance, with a fixed value. So when we go back to our 3 graphs here and look at a shift intervention on x, we now get the following picture you can see here on the slide. So we observe that now these 3 distributions between x and y, they are no longer identical. So after intervening on x, we actually have a chance to distinguish these 3 cases. And in general, so-called interventional or experimental data improves identifiability, so the ability to find out what the actual underlying causal structure is. And this is something we could not do just in the observational case where we did not observe these perturbations. So now we can understand this problem setting a bit better. So we speak of active causal learning when we want to learn a causal model of interest. So say either estimate the whole underlying causal graph or just parts of it, but while being able to actively perform interventions or experiments. So we look at an iterative procedure that is illustrated here at the bottom. So at the beginning, at the first step, we would choose an intervention. So we would say we would pick one of the variables and say we manipulate it in some sense through either shift intervention or do intervention. Then we perform the corresponding experiment that then yields a new data set. So that can be a few or several observations that are obtained after performing this experiment. And then on top of that, we then run our causal discovery algorithm that estimates the structure. And then we iterate. So then again, we have the chance to perform another experiment, collect yet more data, and so on. So this is the general setting we look at. So at the end, you will have a number of data sets from different experiments, also, in other words, from different interventional distributions. So now I said interventional data generally improves identifiability. However, this improvement depends critically on the target and the nature of these interventions we carry out in each experiment. And in real application, experiments, of course, tend to be really costly. So there's a need to perform good interventions in some sense, so that as few as possible are required. And hopefully we can then learn as much as possible quickly about the underlying causal structure. So the main question in this active causal learning setting is, how do we select informative experiments? So how do we choose what variable to intervene on in each round? So in terms of prior work, one can broadly categorize that into two classes. So on the one hand, we have graph theoretic approaches, and on the other hand, we have a number of Bayesian approaches. So these graph theoretic approaches, they typically give bounds on the number of interventions required for identifiability under a number of different assumptions. And they provide intervention selection strategies that then aim to orient, say, the maximum number of edges in the graph. In the Bayesian approach, there generally one selects interventions which maximize a Bayesian utility function, which is often the mutual information between the graph and then the hypothetical sample that the experiment would produce. So here we now take a somewhat different approach, and we build on this invariant causal prediction method. So to clarify these approaches on the left here, so those are papers that already consider this active causal learning setting. But now invariant causal prediction, or in short also ICP, that is just a structured learning algorithm, but it is formulated for the setting where one has access to multiple data sets that came about potentially through different interventions. But now ICP, as introduced in these papers listed here on the right, that does not yet answer the questions what experiments or what intervention should be performed. And this is then exactly the question that we address in the work I'm going to present. So now you might wonder, okay, why is it a good idea to build on invariant causal prediction? So the assumptions are quite flexible in some sense, and it has coverage guarantees on the result. And I'll go into the details of how this method works and these corresponding guarantees in the following. So ICP is, as I said, is formulated for the setting where we have data from different settings, also called environments in ICP. And so these different environments could be intervention settings with known or unknown targets. So the important point in ICP is that we don't need to know where we intervened that then gave rise to the corresponding data set. We just need sort of a number of data sets, and we don't care how they came about. So for instance, we could, for ICP, we could use as a first environment this observational data we already looked at before. And then potentially a second environment could be the one that came about through a shift intervention on X. But again, we do not need to know the fact that we intervened on X here. We just need to know that, okay, these data points come from a different setting than the first set of data points. So now there's one key observation to make here. So previously we just said, okay, what we observe when we now in the slide compare the plots in the first row, we observe, okay, the regression fit is exactly the same. And then when we compare the three plots in the second row here, we observe that they are no longer the same. But now there's an additional observation that we can make here. And for that, we now compare the two plots in each column. So in the first column on the left here, we have that X is a causal parent of Y. And when we compare the two regression fits, we see that these are identical. Whereas for the second and the third column, when we compare top and bottom, the regression fits, those change. And now this observation that the estimated regression fit, or a bit more specifically, the conditional distribution of Y given X remains the same under interventions. So the fact that it stays the same only for the the causal parent here, this is something that is used in ICP. So a bit more formally again, what we are interested here is we consider one response variable y of interest and a set of predictor variables x. And instead of learning the whole graph, we just want to know what are the causal parents of y, and recall that this set is denoted by S star here. So the observation we made in the previous slide is that as long as we avoid intervention on y itself, then we have this invariance of this conditional distribution you can see here. So we look at the conditional distribution of y when we condition just on the causal parents of y. And then this conditional distribution is the same across all environments. Now, this is a fact that has been known for a long time. But now this key idea of this invariant causal prediction method is to turn this around in some sense. And that is to estimate the causal parents of y by finding invariant conditional distributions. So when we have access to data from multiple environments, then we can estimate the set of causal parents by finding invariant conditional distributions. So now one small caveat to this is that, so this invariance, it holds for the true causal parents, but it may also hold for other sets of predictors. And that will depend on actually how your environments were generated to some extent. So for that, we introduced the following definition, or this invariant causal prediction method, and paper introduced this definition. And that is the one of so-called plausible causal predictors. So we say that for a set of variables S, they are plausible causal predictors under a set of environments if this invariance holds, when here again we now look at the conditional distribution of y conditional on now the variables that are in this set S. And in the previous slide, we saw, okay, this holds for the true set of causal parents. So when we condition on S star here, we have this, but other sets S may also satisfy this invariance. Now, how does ICP handle this? So the method needs some statistical hypothesis test for this invariance. And depending on what further assumptions you want to make, there are different options. So for instance, you say, okay, I assume my system is linear. Then you can just test for equality of regression coefficients and noise variances. But then there are other options, for instance, when you say that your system is nonlinear, or when you have time series data and so on. So we need some test that is suitable for our problem setting that tests for this invariance of the conditional distribution. And then H0S will be the null hypothesis that the invariance holds for some particular set of predictors S. And then in ICP, one tests this null hypothesis for all possible subsets of the predictors. And then the final estimate will be the intersection of all those sets for which we could not reject the null hypothesis of invariance. So let me go through an example to clarify this. So here at the top, I'm just again showing you the same description from the previous slide. And now here at the bottom, we have the example. So on the right-hand side, this is the underlying data generating graph. And say the first environment we have access to is just observational data. And in a second environment, we observe shift interventions on X1, X2, and X3. So now what ICP does, it tests this null hypothesis of invariant conditional distributions for all possible subsets of the predictor variables. And here in this example, it turns out that we fail to reject the null hypothesis for two sets of predictors, namely for the X1 and X2 and for X2 only. So this is these are all the sets we fail to reject, or also we'll say in the following that we accept. And then the ICP estimate will be the intersection of these two. So we end up just with x2 here. And in this particular case, this is already exactly the right answer. So x2 is the only causal parent of y here in the graph. So now what is quite nice about this method is that it has a coverage guarantee. And that is that this estimated set S hat is a subset of the true causal parents with high probability. And why is this? So this can be quite easily seen, because S hat would not be a subset of S star had we rejected the true causal set when we tested. I mean, of course, we don't know which set is a true causal set, but at some point we test the true causal set, right? Because we test all subsets of the predictor variables. And now the probability of not rejecting S star is larger than 1 minus alpha, where alpha is just the chosen significance level of this test we use. And that is the case because we know that the null hypothesis is true for S star. So in other words, what we see here at the bottom is that S hat will not contain any false positives, that is variables that are not parents of y with high probability. So now this coverage guarantee is quite nice, but when you run ICP in practice on a set of environments, it quite often returns the empty set. So the empty set is still a subset of S star, so the coverage guarantee is of course intact, but the estimate is also not very informative. So in other words, ICP often does not have a lot of power to detect the true set of causal parents. Now this power can be improved the better, quote unquote, the available environments are. And in general, the estimate improves monotonically with interventions. So what we see here is we have a collection of environment script E1 and a collection of environment script E2. And E2 is a superset of E1. And then the estimate based on E2 will be at least as good as the one based on E1. But now recall that ultimately we're now interested in an active causal learning setting. So we do have the option to collect these environments ourselves and then hopefully to collect them in a smart way such that we'll be as close as possible to S star. So the ultimate question we want to answer is, how can we choose informative interventions? But for that, we first need to settle the question, what is an informative intervention in the first place? And for that, we'll say the most informative intervention is the one after which the largest number of parents appear in the estimate. So now to then develop our methodology, we need one more ingredient, and that is the notion of so-called intervention stable sets. Because these intervention stable sets now allow us these invariance properties of a set of predictors to graphical criteria. And for that, what we'll now do, we'll add these interventions as source nodes in the causal graph. So here in the graph on the right, we'll have two interventions. So the first intervention acts on x0 and the second intervention acts on x4. And now we add them as additional nodes in the graph. And now a so-called intervention stable set is one that deseparates the response from all interventions. So we need that y needs to be deseparated from I, given this set S, for all interventions that are active in a particular environment. So let me go back to the example to clarify this. So here we have two interventions, and now we look at all sets that would deseparate the response Y, from these interventions. So if you haven't heard about deseparation before, just on a very intuitive level, we somehow need to, in some sense, block the flow of information from now these intervention nodes to Y. So for instance, X0 would satisfy this, because then this path from I1 to Y would be blocked, and this other path is also blocked. So the path that goes from I2 to Y, because we have collider, so-called collider X3 here. So in any case, so we get a number of sets that satisfy this deseparation relationship. So X0 alone would work, but we could also add X4 to the set and X3, and then similarly also X1, X4, or all the remaining ones. So now the question is, what do these intervention stable sets have to do with ICP? And here it turns out that an intervention stable set is a set of plausible causal predictors. So to remind you, if we condition on these variables, the corresponding conditional distribution will be invariant across the environments. But we just have the implication in this direction and not the other way around. So the other direction, so that a set of plausible causal predictors is an intervention stable set, that is an assumption we have to make. But violations of these assumptions are quite rare. So they only happen for very particular values of the causal model. And hence, this is an assumption that is kind of not too strong to make. It's somewhat similar to the faithfulness assumptions, if you're familiar with that. So now what have we gained? We can now reason about these sets of plausible causal predictors in ICP through intervention stable sets and through these graphical criteria. And also to clarify, so when we run ICP in practice, there are a number of sets for which we fail to reject the null hypothesis, and for which you then also say these are the accepted sets. So these are estimates of the sets of plausible causal predictors. And so now that we have this relationships, we can actually infer properties of the graph structures and the interventions based on the stable sets, and then use them in the context of ICP. So the first small result that we have is that if a parent is directly intervened on, then it appears on all stable sets. And this is why we then treat direct interventions on parents as maximally informative, because we know then in the absence of estimation errors, if we intervene on a parent, it is sufficient for it to appear in the corresponding estimate. However, having said that, it's not always optimal in the sense that for particular graphs, it sometimes may be better to intervene on ancestors that are further up in the graph, and that intervening on those will yield more than one parent in the estimate. But given that we don't know the graph structure, these settings it's unclear how to detect them from say, the accepted sets in ICP. So hence, the option we see for now is just to say, okay, we treat direct interventions on parents as maximally informative. But now let me quickly go back to our example and let's verify the statement I just made for this example. So I said if the parent is directly intervened on, then it appears on all stable sets. So indeed, here in this graph, we intervene on X0, and it's a causal parent of Y. And then when we look at the stable sets, indeed, we see that X0 appears on all stable sets. And in the end, right, if we now say if those are exactly equivalent to the accepted sets in ICP, so if in the ideal case without estimation errors, then in the resulting intersection of these sets, we would retrieve X0. But for instance, we would not retrieve X1 in this case, which is also a parent of Y. Okay, so now the principle we will follow to answer this question, where should we intervene? The principle will be that we say, okay, we'll try to increase the chance of intervening on a parent, because that is then sufficient for it to appear in the estimate in the absence of estimation errors. So before I go to the particular strategies we propose, let me remind you of the big picture. So we introduce active invariant causal prediction as this general framework. So we again have this iterative procedure where we, in the first step, we choose an intervention target. Then we perform the corresponding intervention or experiment and collect a sample from this interventional distribution. And then this sample will be added to our set of environments. So here that would be script ET. And then we run invariant causal prediction on this set of environments. And then we update the accepted sets and the estimate we get from ICP in each round. And then potentially in the next round, we actually choose the next intervention target based on this previous result from ICP. And then we iterate. So this is the general framework. And now we make several proposals of what to do in step one here. So these are different strategies we'll propose and then compare experimentally in the following. So I said before that stable sets contain information about the graph structure. And perhaps most interestingly for our purposes here is the so-called stability ratio. So for that, we look at the proportion of stable sets in which a variable appears. So for a given set of environments, script E, we have the stable sets. And then for each variable, we check, okay, in how many of these does it appear? And then one can show that parents appear on at least half of all stable sets, and that is regardless of where we intervene. So if the stability ratio of a variable J is smaller than 1/2, we know it's not a parent. The important point to realize is here the converse is not generally true. So we also have that ancestors in general appear on at least half of all stable sets and also so-called non-descendant parents of children. But in any case, already this property shown in the proposition here gives us quite some information. So in practice, we run ICP on the set of environments we have access to. Then we get a number of sets we accept. So these will be an estimate for the stable sets, and then based on these we can compute an estimate of the stability ratio. And so now the first strategy, the so-called erasure strategy we propose, is to say do not intervene on variables with a stability ratio below 1/2, because we know that these variables are not parents, and our goal is to intervene on parents, or at least increase the chance of intervening on parents. And then the second result we make use of is about the stability of the empty set. And that is assuming faithfulness. If the empty set is stable under a set of environments, then we know that none of the interventions in the set of environments were performed upstream of the response Y. Or in other words, if the empty set is stable, so if it's accepted, then the set of environment contains no interventions on ancestors of Y. So how can we exploit that in practice? So here on the slide, I just put for brevity, if after an intervention the empty set is accepted, discard the target from future interventions. But let me elaborate a bit more on this. So what we assume here is that the very first data set we have is, say, observational data. So that is one data set we have. And then additionally, we use the data set that we collected in the last intervention. And then if the empty set is stable over these two environments, then we know that this last intervention we performed, that did not act upstream of Y, or that variable is not upstream of Y. And hence we say, okay, since again our goal is to intervene on parents, we know, okay, this node we just intervened on, we don't need to intervene on it again in the future, so we discard it from consideration for future interventions. And then the final strategy is just say, okay, we want to pick intervention targets from within the Markov blanket. So the Markov blanket in our setting, that would consist of the parents of Y, the children of Y, and parents of children. So hence this also to some extent narrows down the set of possible intervention targets, and the parents are among these sets in the ideal case if we have perfect knowledge of the Markov blanket. So these are in some sense the three base strategies, and then in the following we'll also consider combinations of these. So each strategy on its own just narrows down the set of possible intervention targets, but in general we will still be left with several options. And then the actual intervention target we then just choose uniformly at random among these. Similarly, if we now combine several of these strategies, we'll then take the intersection of the remaining intervention targets and then again choose uniformly at random among these. So now in experiments, so one thing I should stress, so all the results I presented so far, they don't require particular parametric assumptions on the system, so we don't need the structural equations to be linear, for instance. But now for the experiments, we actually generate linear structural causal models. And we look at different sample sizes per intervention. So on the left here, you see the setting where in each round, we just collect 10 observations from the corresponding interventional experiments. Then in the center, we collect 100. And on the right, we collect 1,000 observations per experiment. And then we look at 300 structural causal models. Here we have 11 predictor variables in addition to the response variable of interest. And for each of these structural causal models, we also run the policies a number of times to account for the stochastic components we still have in the intervention target selection. So these are broadly the experimental settings. And then here in this plots, the metric we look at is the average Jacquard similarity. So you can see the definition here at the bottom. So we just look at the number of variables in the intersection between S hat and S star. So S hat being our estimate and S star being the true set of causal parents. And then that is divided by the number of variables in the union of these two sets. And so this metric is equal to 1 if and only if S hat and S star coincide exactly. So what we see here in terms of performance, so first of all, in the real world, experiments tend to be costly. So you would want to have good performance in as few iterations as possible. But then still, depending on your budget, in practice, it will still differ, like how many samples or how many observations you can allocate to each experiment, and also how many interventions you can run in total. And what we see here from the results is that then the choice of the optimal strategy or policy will exactly depend on your budget and where you lie in terms of these number of iterations and number of samples. So what we observe in general here is that for the strategies where we rely on an estimate of the Markov blanket, so these are the ones with the dotted lines here, you have quite a good initial performance in the first few iterations, but then poor performance for larger T, so larger intervention numbers. And that is independently of what other strategies are used. So we get this estimate by performing an L1 regularized least squares regression on all predictors, so the lasso. And we picked the regularization parameter for each structural causal model by cross-validation. And in the first few iterations, the policies then quickly identify those parents that are contained in this estimate of the Markov blanket. However, it also happens quite often that not all parents are contained in the estimate of the Markov blanket. And that is why then the corresponding policies, they become stuck at performing non-informative interventions because they never intervene on the parents that are not contained in our estimate of the Markov blanket. And so as a result, for many of the structural causal models here, not all direct causes are recovered, even after a large number of interventions. So this problem is alleviated to some extent for larger sample sizes when the lasso yields a better estimate of the Markov blanket, but the problem does not go away entirely, even for 1,000 observations per experiment. So this is in practice really one problem we observe with this Markov blanket idea, because in some sense the reliance on this estimate of the Markov blanket is too strong and then hurts us in this sense. Now, in principle, these other two strategies I was introducing, they may also be subject to estimation errors. So for the empty set strategy, for instance, we could envision a setting where the empty set is wrongly accepted after we actually intervene on a parent. So when we should not accept the empty set. And then we would discard this parent from future interventions. And this is a problem of statistical power. So the alternative is true, but we still fail to reject the null hypothesis. And this problem is also attenuated for larger sample sizes and also stronger interventions. And then finally, for the ratio strategy, when we falsely reject stable sets and wrongly accept unstable sets, that would also bias this estimate we compute for the stability ratio. And then also we would, for some parents, we might get a wrong estimate of the stability ratio and also then not intervene on these parents. So to sort of summarize this, in principle, all these strategies, since they try to narrow down the set of possible intervention targets, they are subject to these different estimation errors. So in general, you could say, okay, if you have no constraints on how often I can intervene, then you should always just do the random policy, because that is not as affected as the other policies by these estimation errors. However, now what we see for smaller t, all the proposed, or almost all of these proposed policies clearly outperform the random strategy. So this is just the red one. And I think I haven't mentioned that, but it's probably clear from the name. So the random strategy would just choose intervention targets at random, and it would not narrow down the set of possible intervention targets in any way. And so furthermore, we observed that the gain over the random strategy, that increases the larger the sample size is. And so for our experimental settings, so the one we considered here, we found that the performance of this empty set strategy, so that is actually the most robust ones. So it outperforms the remaining policies over a large range of intervention numbers and also for the different sample sizes. And then using the Markov and or this ratio strategy in addition, so that only yields clear improvements for the larger sample sizes, but not for very small ones. Now, one thing I would like to stress, so these sort of caveats and potential failure cases, so they only concern the selection of the intervention target, but this ICP error control, that will remain intact over all iterations. So that is not affected by this, because that is just the plain ICP algorithm we then run on the collected environments. And that is also something we'll see in the next slide. So here we perform a comparison between AICP with the empty set strategy and the so-called ABCD strategy. And so we choose this strategy for comparison because it allows directly learning the parents of the response, and hence it lends itself to a more fair comparison than the methods which estimate the full graph. However, having said that, so the comparison is still not entirely straightforward because the methods still make different assumptions. So for instance, ABCD requires a very large initial observational sample, but then for the interventional samples, the sample size could be as small as 1. Now, AICP, in contrast, would not need a large observational sample, but it is regression-based and needs more than 1 observation per intervention. So what we did here, we established a middle ground by providing both methods with an observational sample of size 1,000 and then 10 observations per intervention. And now in these plots, we compare the two methods in terms of the Jacquard similarity on the left and the family-wise error rate on the right. So that is the probability of having one or more false positives in the estimate of the causal parents. And this is exactly what ICP should control. So when we compare these results, so let's first focus on ABCD. So by using this observational sample in a smart fashion, let's say, ABCD shows better results in terms of the Jacquard similarity in the first few iterations, but then it does not approach a Jacquard similarity of 1 for large T. So even after 50 interventions, it hasn't reached a Jacquard similarity of 1. And now this good initial performance comes at the cost of false positives. So this is what you can see in the plot on the right. And those false positives are only reduced somewhat as T increases. In contrast to that, so AICP remains conservative in the first few iterations. So we can see that by this having the very low Jacquard similarity at the beginning. So at the beginning, as the environments are not yet informative enough, we often actually get the empty set through ICP. So this problem I was talking about earlier. But then the power or the Jacquard similarity here increases quite quickly with the number of iterations, and then also approaches the Jacquard similarity of 1 after roughly 20 interventions. So then we're actually exactly recovering the causal parents. And then when we look at the plot at the right, so the dashed red line here is the level at which AICP is run. So we have this built-in control that the resulting final estimate should not contain false positives, with now a probability here in this case of 90%, right? So 1 minus alpha. And indeed, we see that empirically, so that is the yellow line here at the bottom, that the error control is indeed met. So we have we don't retrieve any false positives here. So with that, I'd like to conclude. So in a setting where you can perform intervention actively that improve identifiability and hence power to detect the causal parents, we believe that it's beneficial to use a method with a false positive control such as ICP. And as we've seen, power is then improved relatively quickly, while the error control remains intact over all iterations. So now there's something you may have noticed, namely, so the goal of the overall method is to find the causal parents of a response variable of y. But also when we choose the intervention target, we said, okay, we want to increase the chance of intervening on the parents of y. And for the ratio strategy, for instance, we showed that parents retain a stability ratio above 1/2. However, then we do not use this knowledge to compute the ICP estimate. So that is just the plain ICP algorithm we run on the generated interventional samples. So the question is whether there's a chance to improve ICP by exploiting the knowledge where the intervention took place. So again, this is also something ICP is completely agnostic to. However, on the other hand, this is also something that makes ICP quite robust to off-target effects. So in practice, in a real setting, you may not often be able to control it that precisely where you intervene, and you may actually not affect just the variable you aim to affect, but also a number of different ones. And then actually using this knowledge where you intervened may hurt performance because it's then incorrect in practice. So not using this knowledge is also, in that sense, a robustness property of ICP. So it's a bit unclear whether it's desirable to change ICP, because then potentially it would also affect this error control we saw. And then finally, I hope to have shown that invariance can be used successfully as the underlying principle in active causal learning. And in fact, in terms of future work, we think that the intervention stable sets may actually allow us to infer further properties about the graph structures. So we now found a couple and exploited them, but potentially there may be more such properties that such that there's still room for improvement in improving this framework of active invariant causal prediction by developing further particular strategies. And with that, I would like to thank you for your attention, and I'm happy to take questions.
Yeah, many thanks for your interesting talk. So for the audience, if there are questions, you can paste them below the live stream. There is a chat button, and there you can paste your questions or also comments. And now I see there are someone. So the first question is, what happens for temporally changing cause graphs and cyclic graphs?
So I didn't get the last word. So temporally changing and then?
Causal graphs and cyclic graphs.
So for just like temporal data, there's this method of sequential ICP. And so in principle, one could then combine the strategies we develop with that version of ICP. So that is, I think, a connection that should be relatively easy to make. Now for cyclic graphs, so far there's no sort of invariant causal prediction version for cyclic graphs. So I think that is then a bit more of an open question, how to run this for cyclic graphs.
Okay. More questions?
Yeah, maybe I can bridge the gap. So many thanks for your talk. So obviously the ability to identify causal predictors is really crucial in many, many healthcare applications. So from our experience, we often get really excited about new methods that are presented, and then the practical applicability is really the challenge because model assumptions break or we don't have enough data, etc. So I was wondering if you have some more or less generic practical hints on how to approach a new problem, I guess, with this theoretical.
So I didn't quite catch the end of the question, whether I have just like practical thoughts on this or
general recommendations in terms of practical applications, theoretical framework, which is theoretically really exciting, but yeah, again, from experience, a lot of really interesting methods break in our domain. So I was wondering if you have some insights.
Yeah, I mean, one thing that comes to mind, so what we did like previously were like to perform like large simulation studies where we also run methods in settings where the assumptions are not satisfied, to understand a bit better which assumptions are really crucial and which are not, because sometimes a method has a particular assumption because it's maybe needed for a particular proof technique, but it turns out, okay, in practice, the method is maybe robust to a violation, and in contrast, other assumptions are really crucial. So I think like also more like on our side of like who write these papers, it's important to perform like a proper analysis of what are the failure cases. And I sort of try to mention this a little bit here by kind of mentioning all these like potential estimation errors that could then like bias these, for instance, this estimate of the stability ratio, and then sort of lead to choosing or making a mistake in practice. And I think from that you can, to some extent, understand a bit better whether in practice what setting you fall into. So for instance, if you know, oh, I have a very small sample size, then you know, okay, this has implications for statistical power, so I have to be careful with this methodology because sort of it requires, say, a large statistical power. So I'm not sure whether this answers your question, but I think that to some extent it's important to sort of, sketch out these failure cases and then also try to connect this to the knowledge the practitioner has about his or her data, like where, in what spectrum it falls into.
Yeah, thanks. And is there so if somebody wants to get started working on this, is there any go-to points, you know, to tutorial or something that would?
So just for like causal inference in general?
Yeah.
So I think there's this recent book that's called Elements of Causal Inference by Jonas Peters, Bernard Churkoff, and Dominik Jancic. So I think that is quite a nice introductory textbook. It's somewhat geared to some extent to also structural learning, which I think maybe previous or other books on causality, they're not so much about structural learning, but more about the estimation of causal effects. So I think especially if you're interested in this problem of estimating the underlying causal structure from data, then I think that's a good resource.
Okay, thanks. And maybe for you as an expert, what would you want to see in the next 5 years as a major breakthrough in these fields?
Oh, that's a good question. So I think now I also, because this is quite recent work, so we're quite excited about this active setting. So I think one limitation in some sense also about this work is that we still need several data points per experiment that we perform. But I think then in many application settings, like collecting a large sample per experiment is very costly. So I think making these methods perform better on very small sample sizes. So this is something I think that could be very relevant and useful practice.
Sounds good.
So I have one last question. So what is the size of quarks you can handle at the moment? And I can imagine that the computation of the subset S become more expensive in the number of predictor variable X becomes too large.
Yeah, that's exactly right. So, now for these experiments we performed, for the results I showed, we did like 11 predictors. I think maybe you can run it up to 20 without having too many issues. But then indeed, that's a drawback of ICP itself, because it needs to consider all possible subsets of the predictors. So to some extent, you could say, okay, if you have a very large sample size, then you could do like additional tricks and like have like do a pre-processing step that sort of prunes the set of predictors, again, using similar ideas like excluding an estimate of the Markov blanket and then running on top of that. But for small sample sizes, this is exactly something we saw that is often like too unreliable. So for very large P and small sample sizes, there's also definitely still room for improvement and further work needed to make this more practical computationally as well.
Yeah, so thank you very much for your answer. So then we are at the end of the talk and also of the data science seminar for today. Yeah, thank you for being there, and hope to see you somewhere soon.